Yes, if you look closely, you can in fact see me slowly melting the insulation on my garage door. When I put in that insulation, lots of people said, hey, you should shield that from the heat of the torch, and I agreed. That is something I should do, and I always meant to put something up there, and then I never got around to it. And well, now that section of the door went from R10 to R9.7. Maybe now I'll remember to do something about it? Probably not. Hello Internet, my name is Quinn and this is Blondihacks. I'm back on the Pennsylvania A3 switcher locomotive build today, and we've got a very exciting piece of the boiler to build today. It is the shell. This is a very defining feature of not just the boiler but the whole locomotive. So it's going to be a lot of fun, a lot of cool operations in this one. Let's go. I'm going to start by backtracking a little bit today. You may recall if you watched the previous video that I flipped two of the holes on my backhead because I misread the drawing, and I appreciate so many of you giving me the benefit of the doubt on that one and saying that the drawing was wrong, but I gotta stick up for Kozo here. The drawing is actually correct. It's showing the entire back of the boiler, not just this part. So the double solid line that you see there is actually the outer firebox sheet, and the flange on the backhead is shown as a dotted line if you look closely there. So this was definitely 100% my fault. And I was going to leave it, but many of you had very good questions about this error, such as will it interfere with the fire door or other similar issues, pressure gauge and so on. But there was one really helpful comment, and you know who you are. Thank you. You saved me a lot of grief. Someone pointed out that if I put the water gauge on the other side, as I was planning to do, it's going to foul on the quadrant. And the quadrant is a little bit analogous to a gear shift in a car. It doesn't actually change gears. Of course, locomotives don't have transmissions. What it does is it modifies valve timing, but it serves a similar purpose in that at higher speeds, you can change the valve timing for greater efficiency, similar to what higher gears do in your car. And as you can see, the water gauge would absolutely not fit on the other side without moving the quadrant. And to do that, you're talking about rearranging half of the mechanics of the valve gear, and that's just going to spiral way out of control. So that's a deal breaker for my plan. That means I have to fix the backhead. I briefly considered rebuilding it from scratch, which would have taken about a week, but I think I came up with a way to fix what I have. So I'm going to start over here on the mill by setting up some of the leftover oak from the formers. These things make pretty good sacrificial parallels. They're planed, so they're reasonably parallel top to bottom. The hard part of this is going to be recovering my setup so I can locate the new features. So I was going to start by centering it up using my indicator holder for the spindle nose that I made. I have a video on making this. Unfortunately, the new mill's spindle nose is ever so slightly larger than the old one, so I'm going to have to modify this tool. That's unfortunate. I was looking forward to using it. Instead, I'll go to the big guns. I have the coaxial indicator, which goes in a collet, and thus is agnostic to spindle nose diameter. I'm going to center up on the fire door hole. I think that's as good a reference as any. I don't have a lot of references on this part, unfortunately, but I can get reasonably centered up on this. Now, this was a hand-fitted part to a sheet metal piece, so it's not going to be perfectly round, but I got it to within about 5 thousandths here, so that's pretty good. And that's going to kind of act as a 0 on this part. And then I need to get it aligned vertically, so I take the coaxial indicator out and I put my wiggler pointer in there. I still have a faintly visible scribe line running down the center of the part, so I'm lining my pointer up on that. So tap in one end of the pointer on the scribe line. And of course, by doing that, the other reference has moved slightly as well. So I went back and forth between the coaxial and the pointer until I had both references reasonably aligned. And then I had an origin on the part and I knew it was vertically aligned to the mill. To verify my setup, I put a gauge pin the same size as the water gauge bushing in the spindle there. And I translated to where the drawing says it should be if it's mirrored, which is what I did with it. And that aligns quite well. So I think my setup is sufficiently recovered here. It's within a few thousandths anyway. So now in principle, I should be able to just translate over onto the x-axis the opposite distance, and this should be the correct location for that bushing. The thing I was worried about though was interfering with that rib there, the reinforcing rib, and unfortunately it does interfere. Those ribs are not perfectly symmetrical. They were laid out by eye, and I wasn't trying super hard to get them perfectly symmetrical because there was no hole over here, so it didn't matter. And well, now it matters. I don't want to cut into that rib, so I moved the bushing up just enough to clear that rib, which ended up being about 1/8 of an inch. And I think I can compensate for that vertical displacement using the plumbing of the water gauge. It's not a perfect solution, but that's a much smaller problem than the one I had, so I will take it. I also need to flip the blower pipe hole, and that one was easy because there's plenty of extra space there. So now I've got 2 blower pipe holes, one of which is incorrect, and 2 water gauge bushings, one of which is incorrect. So the plan is I'm going to add the water bushing in the correct place, then I'll put a blanking plug in the other one, a flush mounted one. And as you can see from the photo here, that should not interfere with anything. It'll just be like a future expansion port. Saves me having to drill that out and repair it. Then I went ahead and turned kind of a reverse boiler bushing, it's flanged on the back, to plug the incorrect blower pipe hole. And I'm going to solder the new bushing and that plug into place here. Here's a fun fact about locomotive boilers while we're waiting for this silver solder to flow. Kozo has done a number of things to simplify the design of this boiler, and one of them is that he made the barrel cylindrical. I'm not sure if the original A3 had a cylindrical barrel or not, but most later locomotives had conical barrels. The reason for that is because at the front lower corner, the furthest place from the coal fire, the water isn't really getting very hot, and in fact it's acting as kind of a heat sink and reducing overall boiler efficiency. So cylindrical barrels were replaced with conical ones because that effectively eliminates the space where that cold water would be sitting. But a conical barrel is much more complex for the beginner to make, hence Kozo's design. You can see how that blanking plug has blocked off the rogue hole there. And once that's painted, you'll never be able to see it's there, I don't think. So I feel good about that repair. Those new joints all look good, so I don't think that will leak. And those are made of bronze, of course, because they're all boiler parts, just like anything else. So I feel pretty good about that repair. I think this has recovered things sufficiently that I'm back to working by the book again, and that's, I think, a good feeling. All right, now for the reason that we're here, and that's the boiler shell. I've got this great big piece of copper here, purchased specifically for this part, and I'm going to start by rough cutting the copper that I'm going to need to roll into the shell here. I'm going to do this over on the bandsaw. This is a sufficiently wide part that I couldn't quite get all the way through it using the throat on my little saw here. Even by cutting from both ends, I was left with a section in the middle that I couldn't get through. And the kerf from this bandsaw blade is thicker than my hacksaw and thicker than my jigsaw. So to finish the cut, I went to the last resort of the scoundrel, and that is the Dremel. I just scored the remaining area there, and then I was able to just fatigue it off like so, and job done. Now a bit of a diversion here. I'm going to make a fixture to do the remaining machining on this boiler shell piece. I've got a chunk of 2-inch angle iron here. I'm cutting a chunk off of that, and I'm going to make 2 what I'm going to call sheet metal clamps. I'm going to all the trouble to make these because this is something I've wanted for quite a while. I machined all the surfaces of these flat, and I put some slots and some other fixturing holes in them to allow me to use them in various ways, as you'll see here shortly. So there's the 2 plates there. These are going to help me clamp on large pieces of sheet metal in various exciting ways. First use of that is going to be here. I've got my fixture plate on the mill table to space the piece up above the table, and I'm going to use one of my sheet metal clamps there to fixture this edge here. And that's going to hold the piece securely so that I can square up my saw cut on that end. Conveniently, this piece of copper is the exact same width as my fixture plate, so I was able to kind of get it square just using the edges of the plate there and tapping that straight. And then I machined this edge here nice and clean. Of course, you could also just file these edges to your scribe line, but you know, if you got the fancy machines, might as well use them. I'm keeping tabs on my dimension here in a couple of places, make sure things are staying straight. Then I flip the part around and I indicated in the edge that I just machined here to get it parallel so that I end up with a parallel cut. And I double check that I'm square on this side edge here. 2 of these side edges are factory edges, and I didn't want to assume that they're square. They usually are, but not always. Alright, but now let's get weird. The 2 short edges of this piece need to be machined down to length as well, but Kozo also specifies a 5-degree angle on these edges. And I'm sure he intends you to simply file to an approximately 5-degree angle. The purpose of that is to make the edges line up nicely and get a tighter joint when you roll the shell. But I thought, how would you do an accurate 5-degree angle on a piece of sheet metal if you needed to? And then I couldn't get it out of my head, and then I had to try it. So I've got my little angle table here set to 5 degrees, and I've got my fixture plate here, and I've modified it to allow me to mount the fixture plate onto the table. The holes are off-center for reasons that have to do with mounting this plate on my mill table. Don't worry about that. But the point is, I've modified this plate here. This is a fixture plate from Dayton CNC Products. I really, really love this thing. So I can mount the fixture plate to my angle table, and now I have an easy way to set my sheet metal at a 5-degree angle relative to the mill, again using my sheet metal clamp system there that I've just made. Over on the mill, I start by indicating in the edge of the plate there to make sure that my cut is going to be parallel to the table. So I just tap that in. Now I can clamp the sheet metal once again to my fixture plate, and I'm going to use the fixturing pins that come with this plate along with a parallel to get the right spacing from those pins to get the sheet metal square to the table here. Those two long edges have been machined parallel to each other, so they're now good references to get a square cut on the remaining two short sides. And I've got some holes on the edges of those clamping bars there that I can use, and away we go. So I'm machining the piece down to length on this dimension and also putting the 5-degree angle on each end at the same time. And I cannot stress enough that this is a completely ridiculous way to do this operation. You could certainly absolutely just file this to a scribe line, and I'm sure it would be sufficient for the operations that are to come. But you know, I got all these fancy tools, and I got all dressed up, I got the apron and everything. I mean, I gotta use it, right? With the piece at dimension, the next thing Kozo has you do is deceptively clever. He has you put 3 equidistant scribe lines across the part. Now the cleverness of this is once the shell is rolled, you will now have 3 longitudinal reference lines automatically placed 90 degrees apart on the final shell. And that's extremely useful for future setups, as you'll see. If you don't do that, then getting those scribe lines on the final shell is actually pretty tricky. You have to try and scribe it on a surface plate, and it doesn't come out super accurately. This is something I did do on a previous boiler that I made. It was a horizontal stationary boiler, and my scribe lines for reference were not very good because I did them on the round shell. So doing them before you roll the shell is very clever. Next, one of the offcuts is the perfect size to start with for the second piece that we need here, which is a rivet strip. This is the strip that closes up the seam in the rolled shell. It's both riveted and silver soldered in place. I'm once again measuring and rough cutting this to size on the bandsaw, and then I'm going to mill it to final dimensions using my sheet metal clamps here once again, this time just using them to extend my vise jaws. I've got a parallel down there that's thinner than the stock that's going to keep it level. This setup is actually a good little teaching moment for clamping geometry. The way these clamps are holding that part is actually not ideal. You can see how they're closer together at the bottom, and that's because unsupported like this, the vise jaws just press the angle iron pieces together at the bottom. And what that means is that the piece is actually being held along the bottom edge, not the top edge, because of that angle. And ideally, you want the clamping force to be along the top edge, right under where the milling cutter is there. In this case, I'm getting away with it because it's a very short piece and it's a light cut, doesn't need a lot of holding strength. For better clamping force, you could do something like put something round at the top of the movable vise jaw, between the jaw and the angle plate, and that would force it to clamp along the top edge. Even better would be to modify those angle plates so that they bolt to the vise jaw and thus move in parallel with the jaws. With that all squared up and on dimension, I can move on to the first exciting step, which is rolling the shell. And I'm going to do this on my slip roll here. This is one of those cheap 3-in-1 sheet metal machines that you can buy from all the places. Comes in many different colors, depending if you get it at Harbor Freight or Grizzly or Princess Auto or wherever. I'm doing a little test here on a piece of unannealed copper scrap to make sure that the roller can handle the thickness of this material, and it does indeed handle that very well. Now, I don't have a lot of slip roll experience, so I consulted with my friend Ron Covell, who's done more sheet metal work than everyone else I know combined, and he had some great tips for me. So the first thing I'm going to do is anneal this entire sheet, but not for the slip roll. I'm going to anneal it for a completely different reason here that you'll see in a moment. This took a while because it's a big piece, but I've got a good hearth and a big torch, and I got the whole thing glowing red, and then let it cool down. A lot of people asked about quenching copper. You absolutely can quench it to just speed up the cooling down. Copper doesn't harden when you quench it, but with a flat piece, you're likely to warp it doing that, which is the only reason I don't. The reason for that annealing is the first tip that Ron Covell gave me, which is to pre-curl the edges by hammer forming them. Slip rolls, of course, can't typically roll all the way right to the edges, so if you're trying to make a perfect cylinder, as I'm trying to do, then it really helps to pre-curl the edges. And I'm just hammer forming using this wooden form here to check the radius. That's the front tube sheet backer, which has the same diameter as the finished interior of the shell. With those edges pre-curled, the next step is to set the drive rollers to the correct tension. The bending roller is moved all the way out of the way on the back there. I'm also trying to keep the material as square to the machine as I can here. The two things that can go wrong with slip rolling are you end up with a corkscrew or a cone. The corkscrew happens if the material is crooked. I find a level is helpful for keeping the drive roller straight as I tighten it down. You want to tighten it to the point where you can no longer pull it out by hand. That's the tip I've been given on that. Once you can no longer pull it out by hand, then the drive roller tension is correct. And you can just kind of roll it through with, again, the bending roller not touching the material, just to make sure that your drive is good. And once that's good, then you can start applying some pressure with the bending roller. And once again, the level is helpful for keeping the bending roller straight, because if the bending roller is crooked, you end up with a cone. And that can be a feature if you're trying to roll a cone, which you can do with a slip roll, but if you're trying to make a cylinder, you got to make sure that bending roller is straight. And from here, I'm just rolling it back and forth, going a little bit at a time. I'm counting the turns on the bending roller there, which helps keep it straight as you go. I do not have a lot of slip roll experience, as you can probably tell. Everything that I'm doing is a combination of things I learned from Ron and things I learned from watching various other YouTube videos on how to use slip rolls. I'm taking my time here and going a little bit at a time because you don't want to over roll it. That's much more difficult to fix than under rolling it, so I'm going nice and slow. There's no hurry here. If you don't have a slip roll, you can also do this by hammering it over, say, a piece of pipe that you've turned to the correct ID. That will require a lot of annealing, just like any other hammer forming operation, but you certainly can do it that way. But I bought this machine pretty much specifically for this project, so I wanted to give it a try, and it seemed to work really, really well. I got the shell pretty darn round. I just went till the edges met up pretty well, and then I was able to pull it off of there. Then to tidy up that edge, I annealed it and did some hammer forming around a piece of round stock here. I had a little bit of a corkscrew in it, which I was able to straighten by hand after annealing, and then a whole bunch of hammer forming later to tune up that edge, and it closed up nicely. Once I got the radius correct all the way around, the joint just naturally closed itself up. I also used the front tube sheet backer once again to work my way down the seam and hammer everything into a better shape as I went down. That worked quite well as well. I think I annealed the shell 1 or 2 more times during this process just to keep things moving. Once I was happy with the fit of that joint, Kozo suggests using some wire to hold things tight and round through the next few steps, and I gave that a shot and it worked okay, but I wasn't very happy with how tight I could get it, and it wasn't holding the seam very well. So instead I switched to hose clamps, and these worked extremely well. I was able to close that gap up really nicely, and it held that joint really, really firmly. So I strongly recommend the hose clamps. The other advantage is you can take them on and off as much as you need, which is helpful during some of these upcoming steps here. That seam is looking good. Now we got to get the rivet strip in there, and this is going to be tricky. I'm going to make a fixture for this purpose. I've got a piece of 1-inch square bar mounted up in my drill press with the very wobbly chuck in it that I still have not investigated. And I'm going to put a couple of generous clearance holes in it for some 1/4-inch threaded rod. You'll see how this matters here in a moment. Then over on my mill table, I can put this bar up on some 1, 2, 3 blocks to get the height that's required, and I can put some threaded rod down through the bar there to hold it down to the table. And what this is going to allow me to do is elevate everything to the point where I can fixture it. So I've got my rivet strip on there, and then I'm going to be able to slide the tube over it and line everything up there and do all of my operations here. Now, lining everything up is the tricky part. So here's how I went about that. I've got some center lines scribed on the square bar there, and I'm cleaning it up with some isopropyl alcohol so that the super glue will stick, and I'm going to super glue the rivet strip down. And I've got center lines both directions on the rivet strip as well, so I can get that rivet strip perfectly centered on the square bar. I clamped that down and gave that a good 30 minutes to set. Now I've also scribed the outside edges of the shell on that square bar, again referenced from the center of the bar. So I can slide the shell on there and line up the edges, and then the seam in the shell is the center line on the x-axis. And in theory, if I did all of that right, then the shell should end up perfectly centered on the rivet strip underneath, even though I can't see anything. With that all lined up, I can clamp the shell down to the square bar, kind of pinning the rivet strip underneath, which is also superglued to the bar, and everything should stay put. And then I can drill through both pieces and get all 8 of the little rivet holes that are required to join them together. Now using my pointer in the spindle, I can line up the y-axis on the seam there, and I ran it down to both ends, and I tappy tap tap to the ends back and forth until the pointer was running straight all the way down the seam there. The secret sauce to this setup are the oversized holes in the square bar. When I'm tapping it in, what's moving is the square bar relative to the threaded rod. That means that the bar is moving relative to the mill, but the tube is moving with the bar because it's clamped to it. And of course the threaded rod can't move relative to the mill because it's in the T-slots. So when you're designing a setup like this, make sure the right thing is going to move when you tap on it and that something can move so that you can tap it in. It's really important to get this seam as straight as I can because there's not a lot of room for error here. These are 1/16 rivet holes that are 1/16 apart, so I got to be close here. Then I use the edge finder to pick up the edges of the shell, and that gives me the center of the entire shell here on X. And now I can lay out my bolt pattern, or rivet pattern, I guess. I start by putting a tiny little dimple with the center drill in each position so the drill won't wander off the curved surface there. And then I come in and I drill all the way through with this 1/16 drill, which is basically a close-fitting clearance size for 1/16 rivets. I drill through until I see steel chips come up on that drill, which means I've reached the square bar underneath, and I move down and do all the rest of them. I gotta say, this new mill with the 4,000 RPM spindle sure makes drilling these tiny holes a lot easier. You can feel it cutting better and much less risk of exploding drills. Next, I countersink each of those, and this is not just aesthetic or removing burrs. This is important because this is the space that the rivet will be peened into and makes it into a secure joint. I countersunk those basically as much as I had space for there to make sure that the rivets will have space to grab. And I can pull it apart and you can see the rivet strip underneath, and a little bit of heat will break the super glue. I won't say I got it perfectly centered end to end. My center line on the rivet strip wasn't perfect, but it came very close. Certainly good enough. I'm pretty happy with how that fixture worked out. A quick test fit here to make sure everything is all going to fit. There's all 8 rivets roughly installed there just to see how things are going to work. And I even got the rivet strip nicely centered underneath, so that worked out really well. To peen those rivets now, I'm going to go back to my little fixturing bar, and the little dimple left by the through-hole drilling becomes my guide for drilling the little dolly holes that are going to hold the heads of the rivets. I determined empirically that a number 38 drill 50 thou deep made a little divot that's a perfect fit for these 1/16 copper rivets. So that's going to become kind of a gang dolly, if you will, for doing all of the riveting of these parts. Okay, we're just about ready for silver soldering, so the shell and all the rivets and everything now get pickled because we have to flux everything before riveting so that there's flux between all these parts so that solder will flow between all of them. So that filthy shell gets a good bath in pickling acid and clean water. And for this I'm going to be using the black flux because it's a large part and a large joint. I think the extra working time of the black flux is going to be really helpful here. I've decanted it into a little plastic shot glass there so that I don't contaminate the big container there. It's a trick I got from a viewer. And some out-of-frame fiddling gets all of the rivets seated in there. Then I just line it up until I feel all 8 rivets drop into those divots there, just like that. And now I can get ready to do the peening. For that, I've made this little tool out of some glamorous scrap, hence the creative shape. And what I did is I machined a slot in the end and machined the thickness down to 94 thousandths, which is 1.5 times the rivet diameter. I don't have a lot of riveting experience, but the internet tells me 1.5 times rivet diameter is what you should peen over. So using my flush cutters and this little tool, I can quickly cut all of these rivets to length. I have learned the hard way that it's much better to cut the rivets to length after you've installed them because of course you're making a burr on the end of those rivets. So if you cut them to length beforehand, you spend a lot of time cleaning up the ends of tiny rivets trying to get them to go back through the holes. Then a combination of a punch and a ball peen hammer to peen all of those rivets over. And that joint should be nice and secure now, and I can take the hose clamps off. Quick inspection here, and things are looking good on the inside there. All the rivets look tight, and my flux has mostly survived, but of course I have to touch it up some more here before I go to silver solder. Joints like this that are riveted and soldered are messy because you have to flux everything. All the rivets and everything all have to be fluxed before you assemble it all and before you rivet it all, which means everything's covered in flux by the time you're done. But now I can finally get some solder pieces positioned in there down the length of the joint. You can see I've got it set up on some blocks here that will allow me to heat it from below. I'm actually preheating the top of the shell. For large parts like this, I found it helps to preheat the far side of the part first. That way it acts as less of a heat sink. You've got less of a temperature gradient around the part, and it won't suck so much heat away from your joint, because it can be very difficult to get your joint hot enough on a big part like this. Once that solder starts to flow, I'm using the patented Kozo scratch rod to move the molten solder around, make sure I get good coverage there. I will say this seemed to go okay, but not great. I struggled to get the part hot enough, and more about that in a minute here. After pickling and inspection, my fears were partly confirmed. I did get very good solder penetration all the way down the joint, but a couple of the rivets did not get solder through them. And on the inside here, a couple of spots on the strip don't look like they got enough of a fillet, and I do have a little bit of a gap there. So mixed results on that first heating. I pickled everything again, fluxed again, added some more solder to some of those problematic areas, and did another heating. You can see I've also upgraded my torch tip to the largest one, and I've boxed in the top with fire brick there. This kind of setup really helps keep the heat in. It helps you get the part hotter faster, which makes for a much better and safer joint in my experience. And this heating went much better. I had little difficulty getting everything hot enough. I got solder through all of the rivets except that stubborn pair at the end there. Center joint still looks good, and on the inside the story's much better. I got a nice clean fillet all the way around that rivet strip now, both sides and both ends. The little gap is gone. So everything looking good except those two rivets, so I did one more quick heating and just kind of caulked those rivets with some additional solder there. Now I'm feeling good about that entire joint, so I think we can finally move on. After all that heating and beaten, the shell is a little bit less round than it was, so to fix that, we take the front tube sheet backer once again, cut a little notch in it to clear the rivet strip there, and now we can just hammer this through the pipe to straighten it back out again. The copper is annealed from all that silver soldering, so we don't need to do that. And what Koza suggests here is pushing it through a little bit at a time and then hammering around the edges to kind of true up the circle a little bit at a time. And this seemed to work quite well. As you go down, it gets easier and easier to push that backer through there. And then when you're done, a standard Imperial Hulk punch removes it. Checking the fit now, the throat plate will go thusly, and that joint looks good. That looks like that should silver solder nicely. And then over at the other end, the front tube sheet slides in that end as well. So it looks like I'm on dimension and things are nice and round. So that's really encouraging. I think those joints should solder up nicely when the time comes. Final step is to true up the ends. And to do that, I'm going to use this mandrel. Remember how I made this wood turning mandrel and I was so pleased that I made it all fancy so I could reuse it and then I only got to use it once anyway? Well, I get to use it again. So who's laughing now? Well, I mean, nobody, I guess. It's not really funny. Look, I get to use my mandrel again and I'm excited, okay? So I turned this down to the same size as the front tube sheet backer. And if you're wondering why it says backhead former on it, it's because I actually made the backhead former twice. I screwed it up the first time, so I used that piece of scrap to make this piece, so no dead tree went to waste. The wood disc at one end allows me to clamp the shell in the forejaw without crushing it. That's a nice feature. Then the other disc goes in the other end, and I can put a 1/4-inch dowel pin in my chuck there and support the far side of it here. I did my best to dial it in here. It's a hammer formed shell. It's not going to be super round, but I think I got it to within 10,000ths, which is sufficient for what we're doing here. All we're doing is facing the ends. There's definitely some wobble in the tailstock there because nothing is especially concentric here. It's all wood and hammer formed parts rammed together, but it's running well enough that we can face the ends. The objective here is to face the shell down to final length and of course clean up the ends there. As I go, I'm taking my time to measure the length in multiple places, make sure the ends are staying square, and my goal is to remove the same amount from both ends while getting it down to dimension because I want that rivet strip to stay centered in the middle of it there. So this took a little bit of math to make sure that I'm removing the correct amount and also half the amount from both ends. I deburred each end by using a file on the outside edge and then just spinning the lathe by hand using a deburring tool on the inside edge. Copper makes the worst burrs. You can deburr it 5 times and there's somehow still a burr there. It's nasty stuff. Then to remove those plugs, which was kind of not easy because they're pretty tight in there, I put some wood screws in the end and was able to wiggle the first one out. And the other one that could then be removed with standard Imperial Hulk punch. Unfortunately, that is all the time I have. It took a lot longer to show you all that than I thought it might, so I'm going to have to leave it here. But the shell is formed and it's down to dimension, so I'm very excited to get to this point. You might be wondering why not just use a piece of copper pipe for this, And believe me, I tried. Before starting this boiler, I really looked to find a piece of copper pipe that was the correct dimensions, or at least close enough that I could tweak the boiler to fit, because I was concerned about trying to do this step, but it just isn't possible. There's no copper pipe that you can buy that's close enough to work here. So you got to do it this way. But luckily, I think that went really well. We won't know for sure until the pressure test, of course, but feeling good about those joints. Thank you so much for watching, and thanks to my patrons for making all of this possible, and I'll see you next time.